For period 5, your test is Thursday. Period 3 is the same. Period 6 is on Friday. Your remedial quiz is posted. It is due by Thursday morning at 7 a.m. And I would be happy to check to see how some of you have done if you've already taken it. I personally would go over my quiz inside and out before I took the remedial quiz. With that said, we're going to switch gears now. We're going to introduce nuclear chemistry. And nuclear chemistry is going to be a little bit different than our other chemistry chapters. The district likes you to do it very early in the year, but I personally don't see the fit there because I think it's really important to be able to compare and contrast nuclear chemistry with balancing equations that we did a couple chapters ago. So in this chapter, you want to be able to differentiate between chemical and nuclear reactions. That'll be very straightforward for you. You are all extremely strong at balancing equations. You'll describe the 3 main types of radioactive particles, that is alpha, beta, and gamma. We'll talk about those, and then we'll write balanced nuclear equations today as well. You'll get some practice time in. And then next time we'll be looking at explaining nuclear decay rates, talking about neutron to proton ratios and their importance in determining whether a substance is radioactive. And then we'll be calculating the amount of substance remaining after it's gone through 1 or more half-lives. So these are some of the things we're going to be talking about in this chapter. The beginning of this chapter deals a lot with discovery, and to make it a little more interesting, I found a few videos for you so that you could better understand some of the discoveries that took place that helped shape our understanding of nuclear chemistry. Previously, we've talked about isotopes. What is an isotope? You have a different number of neutrons. So you have atoms of the same element that have different neutrons, and if they have different neutrons, they have a different mass number, okay? We're going to talk about radioisotopes here, which are also isotopes, but they have very unstable nuclei, which will break down, and they will emit radiation that can be harmful to you. Nuclear chemistry is that branch of chemistry that talks about atomic structure in regard to the nucleus and any changes that the nucleus of the atom undergoes. Shown here are some characteristics of chemical and nuclear reactions. We've talked a lot about chemical reactions this year. We know that chemical reactions occur when bonds are broken and new bonds are formed, and we'll talk about that in a little more detail in the 4th 9 weeks. We learned how to balance chemical reactions. We know that an atom on the reactant side must appear as a product or in 1 or more products. We talked about valence electrons previously. You know valence electrons are electrons in the outermost shell. They determine the chemistry of the atom. That's why we spent so much time there. We'll talk more about endo and exothermic reactions, whether the reaction absorbs or releases heat when we talk about thermodynamics, and we do a calorimetry experiment where you burn potato chips in the lab. We'll also talk about reaction rate in the 4th 9 weeks. That's kinetics. We'll look at the effects of temperature, pressure, concentration, and catalysts on reaction rate. We have already looked at temperature as a factor this year because you know that we have heated many reactions in the lab. Why did we heat those reactions? To speed them up, speed up the rate of the chemical reaction. So that's a factor that affects reaction rate. And we'll be looking into more of this as the semester goes on. With nuclear reactions, these occur when the nucleus emits particles and or rays. And here, for the first time, you are going to generate new substances comprised of different atoms. So you don't have to have the same atoms on the left and right side of the equation. Whereas these involve valence electrons only, you can get any of the 3 subatomic particles involved in the reaction. You'll see significant energy changes with nuclear reactions as opposed to the small ones that we've seen previously. And you won't see an effect on reaction rate by any of the factors we mentioned previously. We want to briefly talk about the discovery of radioactivity. In the very late 1800s, a major discovery took place. X-rays were discovered, and this has greatly revolutionized medicine. Many of you have had broken arms, legs, etc. And the first thing you do is you have an X-ray taken. X-rays also can be extremely informative in regard to whether a child is aging faster than what their age says they are. For example, you can do a bone age scan, simply taking an X-ray of a child's hand, let's say a child at age 9. You would expect that child to be continuing to grow quite a bit. However, if the X-ray shows any fusion of growth plates, that suggests that the growth process is going to slow significantly, and that child may be showing a greater age than what they truly are. So these types of X-rays can be very informative in regard to early puberty and other situations that can arise. We're first going to look briefly at the discovery of X-rays. I've got a series of videos. I'll explain that later. All right? And this is leading to the discovery of X-rays, actually an almost accidental discovery, and you'll see where the X comes from for X-rays.
Turn up your eye color with Air Optics Colors prescription contact lenses. Enhance any eye color.
Yeah.
In 1895, the German physicist Wilhelm Conrad Röntgen accidentally discovered X-rays while experimenting with beams of electrons inside a vacuum tube. He was working in a dark room with a tube enclosed in a sealed, fixed black carton to prevent any light from escaping. But when he applied an electric voltage to the tube, he noticed a very sensitive light detection screen in the room started glowing. He theorized that this faint shimmering was caused by a new type of invisible radiation coming off the tube. He named the rays X for unknown. In a series of experiments, Röntgen discovered X-rays could travel distances of meters and could pass through materials such as cardboard and human tissue, but not through denser substances such as metal and bone, which absorbed the rays. This meant dense materials left an imprint on photographic paper, and so the invisible was made visible. The first X-ray image or Röntgenogram was of Röntgen's wife's left hand, showing her bones in a ring she was wearing. On seeing it, she reportedly exclaimed, "I've seen my death." Röntgen's discovery hailed the birth of radiology and paved the way for the use of X-rays in medicine. In 1901, Röntgen became the first recipient of the Nobel Prize for Physics. He donated the prize money to the University of Würzburg to promote scientific studies. Despite his fame due to the X-rays, Röntgen refused to patent his discovery, stating that it belonged to the world. Indeed, it was due to ongoing research that more intense rays were developed, allowing X-rays to become central to hospital diagnosis. Röntgen's discovery also laid the foundation for Marie Curie's discovery of the radioactive element radium, which was widely used for cancer treatment.
All right, so that gives you a little bit of background into X-rays. And many of you, I'm sure, have had many X-rays already. Even when you go to the dentist, they do X-rays of your teeth. I'm stuck. There we go. All right, and And you saw that initial x-ray here of his wife's hand, right here with her ring. It almost looks like it's upside down. And we do know that frequent exposure to x-rays can be very harmful. So whenever you get any body part x-rayed, if you're a woman, they'll ask you if you're pregnant, even if you're like 8. And they also will put any type of lead covering over you to prevent any type of potential damage, because x-rays do cause mutations to DNA. All right, so this is going to then lead into a second discovery. This is a French physicist, Henri Becquerel, and he was studying minerals that emit light once they were exposed to sunlight in a process known as phosphorescence. And just a very brief video here to better understand.
Our next great discovery started in the 1890s with the discovery of an unknown radiation called X-rays. It caused a sensation, and scientists immediately began looking for other substances that emitted strange, perhaps valuable forms of radiation. Over the next several decades, a number of scientists investigated the phenomenon, and together ended up shedding light on one of the great scientific sleuthing episodes of modern science. French physicist Henri Becquerel made the first significant breakthrough. In 1896, he conducted a series of experiments to see if various minerals emitted radiation. One of the minerals he happened to test was uranium. Becquerel's technique was to place different objects on top of an unexposed photographic plate, still wrapped in protective black paper. He would sprinkle the uranium onto another piece of black paper, then enclose the object between the uranium and the photographic plate. Later, Becquerel would develop the plate, and without fail, a ghostly photographic outline of the object would appear. From these experiments, Becquerel was able to prove conclusively that he had found a source for the mysterious radioactive rays that everyone was looking for. That source was uranium.
All right, and we're going to piggyback right on this discovery now. We're going to piggyback on this discovery now because Marie Curie and her husband Pierre were going to look at whether phosphorescent minerals also emitted X-rays, and this would lead to the discovery of 2 radioactive elements that will identify radium and polonium, and their discovery is shown here. Interestingly, Marie Curie is the first woman to win a Nobel Prize in chemistry, and she actually won 2, one in chemistry and one we'll talk about. Let's take a look. Some of these links are not in your notes. Some of the links in your notes were broken. I added these in. I'll repost the notes for those of you who are interested in taking a look.
Did they not know how bad radiation is too?
No, they didn't.
Buster!
And what you're going to see here,
Alexa, ask.
and one thing you're going to see here is they did a lot of experimentation on themselves, which is never advised, something that we certainly don't do in the lab. It's one of the reasons I said that you don't eat the salt that you made the other day. That is extremely dangerous, and it really cost both of them their lives, although his life was cut short when he was hit, you want to say by a car, but it really was a covered wagon.
Marie Curie was a pioneer in the field of radiation research and the first woman to win the Nobel Prize in 2 different categories.
Mary Curie was a towering scientific intellect in a Victorian era when opportunities for women academically especially were extremely few and far between.
Marie Curie was born Maria Sklodowska in Warsaw, Poland on November 7, 1867 to a family of prominent educators.
She had to study undergrad because she wasn't able to be accepted into the men-only University of Warsaw. She then had to leave the country to get a PhD. She was the first woman to receive a PhD degree from a French university.
She came to Paris for her education and met Pierre Curie.
Marie shared lab space with fellow scientist Pierre Curie. They were married in 1895 and had two daughters, Irene and Eve. Marie trained Irene to be her assistant, and in 1935, Irene won a Nobel Prize as well.
Marie Curie and her husband began studying radiation and the properties of uranium.
Marie and Pierre's main discoveries were the ability to isolate the radioactive elements, which came from the uranium-based ore called pitchblende. They discovered two new radioactive elements, radium and polonium, which is named for Marie's country of birth, Poland.
In 1903, Marie and Pierre were awarded the Nobel Prize in Physics, along with Professor Henri Becquerel. Marie was the first woman to win a Nobel Prize.
Curie and her husband were absolutely single-minded in the pursuit of their research. In fact, when they were awarded the Nobel Prize, they refused to go and accept the prize personally because it would interfere with their research.
Pierre Curie died from a horse carriage accident in 1906. Despite this loss, Marie continued their work and was offered her husband's teaching position, becoming the first female professor at the Sorbonne.
Curie's research was key in understanding the effects of radioactivity and quantifying those effects on living cells. She really established the field of radiation therapy for cancer.
Marie Curie made history again when she was awarded the Nobel Prize in Chemistry in 1911. She was the first woman to win 2 Nobel Prizes.
It was through Curie's research that medical use of X-rays became really a possibility.
During the First World War, Marie Curie herself carried many portable X-ray pieces of equipment to the front lines to help the wounded.
Curie founded the Radium Institute to continue her research. Due to her prolonged exposure to radiation, she contracted leukemia and died in 1934.
Marie Curie is such a role model, especially for a woman in science. The impact of her work, the scientific integrity, and the drive that she had was truly an inspiration to all of us today.
All right, so 2 Nobel Prizes, 1 in chemistry and 1 in physics. And again, for those of you who are interested, I'll put the links up and you can do some additional research. And everything that you saw is written there. We're going to take a look at 3 types of radiation, and this is going to allow us to write nuclear equations. They really look a little bit different from chemical ones, but I know you'll be very successful here. We already talked about isotopes, where you have atoms of the same element that have different mass numbers due to a different number of neutrons. We know protons, of course, remains constant. Isotopes of atoms with unstable nuclei are called radioisotopes, and these nuclei will break down and they will emit radiation to achieve a more stable configuration. We'll talk about why that is next time. And this process is known as radioactive decay. You'll see an emission of energy or a loss of energy when one of several types of radiation is emitted. And the 3 most common types are alpha, abbreviated as such, beta with a big B, and gamma as shown there. Again, alpha, beta, and gamma particles, their description, the arrow here that's really pressing in terms of what you need to know. An alpha particle is essentially a helium nucleus where you've got a 2+ charge due to the 2 protons found in the nucleus of the atom, and the 2 neutrons are consistent with the mass found. Beta particles are high-speed electrons with a 1- charge, and their mass is consistent with that of an electron as well. Gamma particles have the highest energy of the 3, alpha the lowest. A photon or a gamma particle is shown here. No atomic number, no mass number, so no protons, no neutrons. Neutral. In terms of energy, this can be a little bit misleading. The conversion is shown here. Note the -13 power for joules. and that's 1 megavolt. I'm a little surprised they put the E in there, because meg is typically just capital M. In any event, the greatest energy would be the gamma, the lowest would be the alpha, and that's consistent with the penetrating power, because alpha particles have the weakest penetrating power. They're blocked by a piece of paper. Beta, blocked by metal foil. And gamma rays are not completely blocked by lead or concrete, so those have the greatest penetrating power, the greatest energy. Rutherford identified alpha, beta, and gamma radiation when he was looking at the effects of an electric field on emissions from a radioactive source. And we've talked about Rutherford previously. What was his other discovery? He had that gold foil experiment, and what did that show? It showed that the protons were confined in a dense nuclear core. And so doing that work, he also discovered alpha, beta, and gamma radiation. And you can show the charges of these different particles in the following way. You have a radioactive source here. You shoot out those particles. You pass them through this narrow slit here. And you see how they react when you've got magnetic plates here, a positive and a negative plate. And this is a zinc sulfide coated screen. The alpha particles would be deflected away from the positive plate and toward the negative plate, consistent with a positive charge. The beta particles would be deflected away from the negative plate and toward the positive plate, consistent with a negative charge. And the gamma rays path are not altered any appreciable extent, and that's because they are neutral with no charge. And we're going to take a look at the alpha, beta, and gamma particles here as we learn to write balanced nuclear equations. That'll be your main objective for today, to write and balance nuclear equations. It's very, very, very easy. It's simple addition and subtraction. An alpha particle, as we said, has the same composition as a helium nucleus, 2 protons, 2 neutrons. The symbol for an alpha particle that we will use in these balanced nuclear equations is helium. The charge is 2+ due to the 2 protons in the nucleus. And let me show you how to write a balanced nuclear equation from words. And you will also see how a product that is formed differs from the reactant and how it is a different atom. So the way we approach this is as follows. You should have a periodic table, and we're going to be in the F block quite a bit here. So that'll be somewhat new. Other than writing the electron configurations, we really didn't deal with the F block to any appreciable extent. It says radium-226. The 226 is the mass number. And radium has the chemical symbol of Ra. And we are told that it emits 1 alpha particle. This is our alpha particle, a helium nucleus. That's probably too little in the back, right? How's that? Is that better? Okay. Your approach here is as follows. This you get from the information that's provided. I'm going to get the atomic number of radium off the periodic table. I've got an atomic number of 88. The sum of the subscripts on both sides of the equation must be equal. The sums of the superscripts on both sides of the equation must be equal. So what plus 2 makes 88? 86. No calculator. What plus 4 makes 226?
22.
Using the 86, I use my periodic table and I see that that is radon. It's as easy as that. And an equation has a plus in there. It doesn't matter if you put the helium before the radon.
So radioactive elements can make other radioactive elements.
Yes.
Since they have half-lives to go through stages.
And we'll talk about the half-lives next time.
How long is a half-life like fixed?
Elements have characteristic half-lives, and we'll take a look at that next time as well. And that's an excellent question. All right, that is a balanced nuclear equation. We're going to write several, but it really is that simple. You need to know that an alpha particle is a helium nucleus. That is shown on your in your notes. You can see here, and I don't memorize, I write the equation and I interpret. I think it's easier. But you can see that the atomic number decreased by 2 with the emission of an alpha particle. You can see that the mass number decreased by 4 with the emission of an alpha particle. Also, the mass number that you get here may or may not match what's on the periodic table. Keep in mind, isotopes of elements exist, and we'll give you an example there. This one happens to match. We also know that alpha particles are not very penetrating. They have low energy, and a piece of paper will stop an alpha particle. There are 2 examples that we want to work through. It says write nuclear reactions or equations for the following. The first one says thorium-232. So again, 232 is the mass number, thorium, and you're going to emit 1 alpha particle. And now you want to figure out the rest and write a balanced nuclear equation. And your next quiz, which isn't scheduled until next week, will open up with an easy question like this. The nuclear chemistry chapter is going to be very, very short, and we'll just squeeze it with gases. Some people do nuclear chemistry earlier in the year. Some people do it much later in the year. There's a lot of places you can put it. Thorium has an atomic number of 90, which I'm getting off the periodic table. How do I figure out the atomic number of the new element? Subtract. So 90 minus 2 is 88. And then 232 minus 4 is 228. 88 is used to identify the new element, and that will be radium. And there's one more example. This is a little tougher, but you're very strong in math and you'll have no trouble with it. It says nobelium-259 releases 3 alpha particles. I like to do this. 3 times 2 is 6, and 3 times 4 is 12. Where can I get the atomic number for nobelium? Periodic table, 102. What plus 6 is 102? 96. And 259 minus 12. Atomic number of 96 corresponds with curium, the element for Marie and Pierre Curie. All right, so you have the alpha particle right here. That's one type of radiation. A second type of radiation is a beta particle. A beta particle is a fast-moving electron. No appreciable mass per se, hence a mass number of 0. Charge of -1. These will need a little more protection, if you will, because they have greater penetrating power. They are blocked by metal. And let's take a look at the nuclear equation that you can write. For example, I-131 releases 1 beta particle. Let's take a look at how to write that. So we have I-131 beta. A beta particle is an electron. And so the mass is 0, -1 for beta. Same approach here. Atomic number for iodine off the periodic table is 53. Now be careful here. The math gets back to like 6th, 7th grade math. What plus -1 is 53? 54. So the atomic number is going to increase by 1. The mass number is unchanged. And this is xenon. I'll say it again. The atomic number increases by 1 with the release or emission of a beta particle. The mass number is unchanged. When you are emitting an alpha or beta particle, you put it on the right side of the equation. If you capture something, it's going to go on the left. We'll talk about that next time. This is a beta particle. Also of interest, I-131 and xenon 131, these are called isobars. They are different elements with the same mass number. You don't need to know that, but somebody asked one time, so I thought I would mention it. The other thing I want to mention here, the change in atomic number, of course, results in a change in identity of substance, and that's because the electron that's emitted during beta decay actually has been removed from a neutron, and as a result, a proton is generated, hence the increase in atomic number. That's more than you need to know. Let's take a look at the nuclear equations that we can write, and then you'll give one a shot to make sure that you're understanding. For example, we have thorium-232, and we're going to emit 1 beta particle. How should we approach this? Okay, so that's 90. Now what?
And just add 1.
So this is?
91.
Good. Mass number stays the same. And what element do you have? Protactinium.
Yeah.
They said it's hard to see the T there. That's what they told me 3rd hour. I think you can see it better here. I'll show you. Let me blow it up. Can you see it better? Protactinium. Yes, you can. You have stinky seat. You need a better seat. There's a great seat right there. Then don't complain.
Have you ever used any of these? You personally?
No. Alejandro asked me if I ever used any of the F block elements, and the answer is no. I've worked with radioactivity before to actually a great extent, but I have never used any of the F block elements. There is a professor at FAU who I have sent many kids down to do summer research with, And he does work with europium and I can't remember what the other one. Oh, terbium. He works with both of those.
Most of these are lab
You
created, right?
pronounce atomic number 111.
Say what?
You pronounce atomic number.
Can I pronounce the name?
Yeah, of 111.
I don't even have 111 here. Is that UU system?
Yeah.
That UU system has been replaced, and I'll show you the new names toward the end.
What's the point of that system?
That was just to put placeholders in, but now they've named them for people and etc. All right, let's refocus here. Again, you can see the increase in atomic number by 1, no change in the mass number. On B, it says uranium-235. Again, work it. You've got 2 betas. I like to work that 2 into it, but you need this written. You don't have to do that squiggly wiggly if you don't want to. How do I get the atomic number of uranium? Periodic table, so that's 92. I'll lay off that color. I know it's awful. I think the red is better. And now what would the atomic number of the new element be? 94. This doesn't change. And that's plutonium, and you can watch Back to the Future. Very good movie for its time. You also can release alpha and beta particles. Let's take a look at this one. It says curium-247 releases an alpha and beta. And again, I would work those numbers together to make life easier. 2 plus -1 is? Positive, no, that's bad math. +1, 4 plus 0 is? 4. No, because there's a plus. You multiply when it's got a coefficient, but these didn't have a coefficient. Bless you. Alrighty, curium has an atomic number of? 96 is correct. What would this be? 95 is correct, and this would be 243.
Why is it 95? Because it's +1. So it goes the other way.
That's correct, because this is, yep,
Oh, we got our American one.
yep.
The element produced is the American.
I would like you to try D. It says curium-247 releases 4 alphas. Up. I shouldn't even give you such a big framework. And 3 betas. Oopsie. That's a 3. Do it. All right, what'd we get?
PA.
It's already signed. All right, so 91, and what's here?
231.
231. And 91 is PA. Okay? Looks good. The last thing I want to mention to you, and then I will give you some time to work on your classwork, is we mentioned a third radioactive particle, and that's a gamma particle. Now, gamma particles are very high energy, short wavelength, due to the inverse relationship between energy and wavelength that we've talked about previously. A gamma ray is not going to change the atomic number or the mass number, so you really wouldn't know if it were there, except that so much more energy would be released than for alpha or beta or the combination of two. So you're not likely to get many problems with gamma in regard to writing out the balanced nuclear equation, but very often gamma emission does accompany these types of radioactive decay, accounting for quite a bit of energy. So what you want to get from the lesson is an understanding of how radioactivity was discovered, the three main types of radioactive particles, alpha, beta, and gamma, and you want to make sure that you are comfortable writing balanced nuclear equations, and that's what you'll get some practice with. I'm going to give you your classwork sheets today. The classwork that you want to be able to do is on the screen. It is shown right here, and I will give you that classwork to work on. You can start it today, and you'll probably work on it a little bit more after the test.